Hello, everybody, and welcome to another wonderful day of quantum mechanics. So last time we left off with one of the big proofs of quantum mechanics, which was black body radiation. Today we're going to kind of show how these ideas of quantized energy can be applied to other systems. And some of these may seem fairly familiar to us these days, but it's really important to kind of illustrate these um, how quantized processes can really affect a wide variety of processes. So one of the big ones that we're going to be talking about a lot is going to be spectroscopy. Spectroscopy is essentially driven by a quantum mechanical uh, uh, phenomena. So the major idea, say on spectroscopy, is that I go ahead and I inject light into a system, or I let light come out of a system, and this is going to tell me a lot about the separation in between um, energy levels within a system. So one of the classic examples of this that was available even around 1900 was atomic emission spectroscopy. So one way to think about this is you take a pure element like neon, you heat it up, and it will slowly release energy as electrons fall um, from high energy states, which again, as we saw with black body radiation, temperature allows systems to reach an excited state. And then they will slowly essentially relax down, releasing light. Now, especially when you're talking about, say, noble gases, you get very nice spectra that come out of these heated elements. And what's most impressive is that unlike black body radiation, where you get a nice continuum of frequencies, when you're heating pure elements, especially pure elements in the gas phase, what you end up getting is single uh, sharp emissions at single wavelengths. So thus you get the characteristic colors of neon lights, which is essentially any um, noble gas that's been heated to high temperatures. So when we're talking about halogen lights, it's the same process, but usually applied to diatomic molecules. But again, this fact that you're going to see single wavelengths, again, really helps illustrate the quantized nature of these energy levels. And this was, again, another big proof that atoms possess discrete energy levels. So I can't just have any sort of excitation allowed, only excitations between discrete pre-existing energy levels. To a certain extent, you can think of this as the precondition for the later Bohr model of essentially electrons existing in discrete energy levels or orbits. This is where it originally comes into play. And again, Bohr was able to express this via his Bohr frequency condition, which should look familiar to what we've seen here, where the difference in between energy levels is given by h nu, which again, you can also provide in terms of wavelength. But again, it's this h nu which we keep seeing over and over again, where we got Planck's constant times the frequency of light, really helping illustrate that the frequency of light is directly related to its energy. Now, one of the big things keeping in mind about spectra is that we can break our spectra up into different categories based on two key features that are very related. First is what portion of the electromagnetic spectrum is being used, and the second is which energy levels are being excited, being changed. Essentially, are we exciting in between rotational, vibrational, electronic, so on and so forth. So the first of our major categories, which we're going to talk about much later, is microwave spectra. So this occurs, not too surprisingly, in the microwave region of the electromagnetic range, and this is related to rotational motions. Similarly, IR or infrared spectra, this is going to be changes in vibrational motion, so two atoms with respect to each other. UV vis or ultraviolet visible range, which is what we're often familiar with in lab. This means that we have electrons moving in and out of valence states. So that's essentially those HOMO-LUMO gaps. That's where we've got electrons moving in and out of highest occupied molecular orbitals. Now, If we go to really high energy range, such as X-ray or gamma ray, at this point, what we're dealing with is changes in core electron state. So now I'm exciting electrons deep in the core electron range out into the valence state. And as you can imagine, this takes a lot of energy. Thus, it tends to exist in the X-ray and gamma ray region. And one of the important things is when you put all of these together, they are essentially the big building blocks of how we identify chemical species. So most chemical analysis are often based on one of these spectroscopic techniques. Pretty much the only thing we're leaving out are things that involve magnetics. Mostly, we're talking about NMR and mass spec. Besides that, these are our major characterization techniques. So it's really important to realize just how crucial A, spectroscopy is, but B, how the fact that we've got quantized energy levels are. Because again, these are all based on the idea of quantized energy states. However, there's one other quick application I want to talk about, and this is taking a step back to thermodynamics. And this is the idea of heat capacities. I like bringing this up because it's a good illustration to thermodynamics, as well as who doesn't love talking about how Einstein changed the way we thought about systems. So as many of you are familiar, if I've got a metal or most solid state species, we tend to have, most metals tend to have observed heat capacities of about 3R, which you can also put in terms of the Boltzmann constant of 3 times Avogadro's constant times the Boltzmann constant. So this essentially comes from the embedded degrees of freedom of rotation and translation. So this is fairly well known. However, something funny starts happening at low temperatures. So at low temperatures, what we start to see is that our heat capacities start to drop. And they don't just drop to an arbitrary level, they tend to drop to 0. And this is a very kind of interesting phenomenon, because something really weird happens at these low temperatures. And we actually have a good insight if we go back to black body radiation. Because what we saw with black body radiation is if the gaps in between energy states were much higher than the temperature involved, we would see no excitation. And something very similar is happening here. As we go to low temperatures, we essentially don't have enough energy to essentially access the full range of states that we do at higher temperatures, which means that I can't get all the same rotational or vibrational motion that I would at, say, room temperature. And because of this, what this means is that if in order to heat the system, I put in a little bit of energy and the temperature just jumps through the roof. That's what we mean essentially by a low heat capacity, because there's no place for that energy to go except for into translational motions. And so one of the big proposals in what's often called the Wonder Year in 1905, where Einstein made groundbreaking discoveries in almost every field of physics, was he took Planck's hypothesis that energy levels are separated by h nu, and then he essentially fit it into our heat capacity equation. And he essentially provided a modified form where we still have this 3R expression for the heat capacity, but now we've modified it by a fun little temperature dependent term, where it's based on essentially the Einstein temperature, which is essentially h nu over k. So it's worth noting that every metal is going to have a slightly different Einstein temperature because each one is characterized by a slightly different characteristic frequency. But again, we have this first precursor term of essentially how close are we to the Einstein temperature. And then we essentially have this dampening term, which has an exponential expression. So just like we found in black body radiation, what this really helps illustrate is that under low temperatures or high energy separations, which is really what my Einstein temperature is telling me. So low temperatures, high energy separations, I'm really not going to be able to access that many states. And this is essentially what's going to start popping out of our system. So what you can do is try and analyze how heat capacities behave as a function of temperature using this modified form. And what we tend to see is at low temperatures, we get, let's be honest, a little bit of an odd expression where we have an exponential as well as this linear dependency on the polynomial dependency on the Einstein temperature. But let's think about what happens if I put in a value of 0 here. So if I put in a value of 0, what happens is my exponential behavior essentially just drops away. And all I'm left with is this polynomial description, which is what we're kind of seeing down here. It's a little hard to spot. But this means if I get really low temperature goes to 0, I have a heat capacity of 0, which is indeed what's seen experimentally. I pump the temperature up, and now some fun things start happening. So what we can do is use a power expansion of our exponential term. So we have 1 plus sigma over t. But what's really interesting is what happens with this bottom expression, where again, we'll have 1 minus 1, and we'll just have a sigma over t. But I'm going to have a sigma over t squared. So this sigma over t squared is going to cancel out with this polynomial expression up front, and all I'm going to be left with is this exponential. Now think about what happens at high temps. If the temperature is much greater than the Einstein temperature, well, then this is going to be a fairly small value, and it's going to approach 0. The term in the exponent is going to go towards infinity, which means that the exponential approaches 0, or the exponential approaches, this expression approaches 0, the exponential approaches 1, and all I'm left with is an expression of 3r, which is indeed our high temperature expression. So again, our exponential just cancels out, and we're left with a term of 3r. So again, one of the reasons why I like to point this out, because it is worth noting, there's much more advanced models that fit our experimental data much better than the Einstein formulation, is that it again shows this importance of the relationship in between temperature and energy separation. If you have a high temperature, we can access all of our states. We see classical behavior. But under these low temperature conditions, whether it's for black bodies or heat capacities, we start to see some of these quantum properties start popping out. So next time, we're going to deal with one of the absolute foundations of quantum mechanics that took black body radiation and ran with it. Another wonderful Einstein paper. It's time for the photoelectric effect. Till then, take care.